Welcome to Dr. Beatty's Chemistry Essentials, A-Level Chemistry made easy. So in this video we're going to be looking at shapes of molecules. We're going to be covering the concept behind shapes of molecules and then being able to use it to explain any given molecule's three-dimensional shape. So firstly, we're going to draw the three-dimensional shape of three different molecules. So we're going to look at carbon dioxide, we're going to look at ammonia, and then we're going to also look at methane. And one thing to be really aware of is how we've constructed a three-dimensional shape here, especially in ammonia. So we've got this wedge that is coming towards us, so the thicker end of the wedge is closest, the thinner end is toward the atom, so it's showing this hydrogen coming at us. And then we use this dash with the longest closest to us and the shortest away to show this hydrogen is going into the screen. So we've got out the screen, into the screen. And this same approaches with this tetrahedral structure, which we'll talk about later. We've got a wedge towards us, dash away. The straight lines mean they're in the plane of the screen. So imagine this is the screen and this is you watching the screen. We just put this at a slight perspective so you can see it. And so we're going to have this nitrogen and solid hydrogen bond in the same plane as the screen. And you can see that it's all following the same line. And then here we have the wedge coming towards us, followed by the dash line going away. And these two electrons, what we call a lone pair, are also in the same plane as the screen, but they are going to be pointing upwards. And you can represent a lone pair of electrons with this lobe, okay? So it's just this weird shape here that's just showing the space occupied by the lone pair of electrons in ammonia. Now, when we're talking about shapes of molecules, we're going to be talking about the shape of the molecule around the central atom. So the central atom in each of these cases is firstly the carbon in carbon dioxide, we've got the nitrogen in ammonia, and then in methane we've got the carbon there. So these are our central atoms. The central atoms also tend to be, as a hint, the first element within a formula. So you can see here for carbon dioxide, it's C first, so that's telling us that's the central atom. And this same thing happens for ammonia and methane. That's just a little hint to help you when trying to identify what the central atom is when drawing a molecule. Now, when we look and talk about bond angles, these are the angles between two bonds, taking the middle being the central atom. So if we call the central atom A, generically, and then any atoms around the central atom B, then our bond angle is a BAB bond angle. And so here, this bond angle would be 180 degrees because it is a straight line. Now, before we explain why it adopts this angle and therefore a shape, we need to understand a very easy principle and one that is intuitive. This principle is that electrons are going to repel each other to be as far apart as possible. And this makes total sense because we know that like charges repel and electrons are negatively charged. So if you put two negative things together, they're going to try and get as far away as possible. And so their angles are going to be as great as possible. And furthermore, the shape they adopt is going to be such a shape in order to get these electrons as far apart as possible. And this is the whole principle behind shapes of molecules and bond angles. And so this flowchart of basically cause and effect explains the shapes that we see in molecules and ions. Now, before we can actually predict the bond angles and the shape that adopts, we need to be able to classify electron density. Now, electrons always exist in an area, and that area is what we call its area of electron density. And there are two types of areas of electron density. There's those electrons that exist in a bond, And there's those electrons that exist in lone pairs. So they're non-bonding pairs of electrons, shown with these two dots in our ammonia example. So we're just going to explain what constitutes a bonding area of electron density. Now, this includes any bonding pairs. They can either be a single covalent bond, double covalent bond, or a triple covalent bond, and all of these all count as one region of electron density. And this kind of makes sense because no matter if you've got one pair of electrons, two pairs of electrons, or three pairs of electrons, they're all occupying pretty much the same space, okay? So they're all one area of electron density, whether it be single, double, or triple. And this is really key because lots of people make the mistake of counting this, for example, a double bond, as two areas of electron density, and then the next thing we look at is going to not actually work correctly if you do so. So if we just take carbon dioxide, for example, here then, around our central atom, we have two areas of electron density, both of which are bonding. Now, with the second type of electron density, lone pairs, we count each lone pair separately. So here in the ammonia molecule, we can see that we have 4 areas of electron density, 3 of which are areas of bonding, and the 4th area is this lone pair up here. And finally, just to conclude, methane here, we have 4 areas of electron density and all 4 are bonding areas. The reason we need to identify the areas of electron density is it's due to the number of areas of electron density that dictates what bond angle you obtain and therefore what shape of molecule you obtain. Furthermore, the type of electron density, whether it be bonding or lone pair, also has an influence on the bond angle that is achieved and also the shape of molecules. So this is really important. So we're now going to start to look at all of the different types of shapes of molecules and their bond angles that are produced from different variations of the electron density. What we're going to do in the rest of the video is look at the different shapes and angles that you get depending on the electron densities that you have around the central atom. So we will need to look at the number of electron densities around an atom, whether or not they're bonding or lone pair, and then that allows us to deduce the shape and therefore the bond angles. Now it's really important that as we go through it, maybe jot down the information in this type of grid. And the first bit, we're going to be zooming into the top part of the grid and then working our way through. So we've zoomed into the top of that table that we've just seen, and we are going to look at beryllium chloride, which is an example of a molecule that has a central atom with 2 areas of electron density surrounding that central atom. So we have our formula here, and as we've noted before, beryllium would be first because that's our central atom. So we're going to draw the beryllium in the centre and draw the 2 chlorines either side of it. Now you can see here we have 2 areas of electron density around the central atom. And this is our first area of electron density, which is a bonding area. And our second is here. So we've got 2 areas of electron density around the central atom, 2 of which are bonding pairs. There are no lone pairs, and the shape that this produces is known as a linear shape. The angle across the central atom, so this Cl-BeCl bond angle is 180. As shown in the previous part of the video, we've got carbon dioxide is also an example of this. And remember, even though these are double bonds, they still count as a bonding area of electron density. So we have our first and our second area of bonding electron density, which makes up our linear shape. For the next shape that can be produced, and this time it's with 3 areas of electron density around the central atom, we're going to look at the example boron trifluoride, so BF3. So boron is our central atom, so we put it in the centre. We're going to have 3 areas of electron density around it, as suggested here. They're bonding areas. And what we end up with is this structure here. Now you'll notice I've drawn just straight lines here, so we know that's in the plane of the screen. So if we looked at our screen on an angle, it would look, BF3 would look like this. And so you can see in the same plane we've got the whole thing. Also you can look at it from a more three-dimensional sort of drawing. And so here we have our wedge for the fluorine coming at us. This fluorine is going away from the screen, and this is here. So we're kind of looking on it at a sideways point of view. The top and the bottom is free in this rotation. But they're all different visual representations for this particular shape of molecule. Now the shape of the molecule is called trigonal planar. Trigonal part of it comes from the fact that the other atoms other than the central atom form a triangle, and planar because they're all in the same plane. Now currently so far both these shapes are kind of in two-dimensional, so 180 came from splitting a circle 360 in half. Here we've splitting a circle into threes, so that 360 divided by 3 is 120 is the bond angle. Remember, the bond angle is the FBF angle in this case. So in the next shape of molecule, we're going to have 4 areas of electron density around our central atom. Now in the first example we're going to look at, 4 of those areas are all going to be bonding areas. So if we take our trigonal planar from previous, so this is a central atom with 3 bonding areas of electron density, but we introduce a 4th area, then as that 4th area of electron density comes from this direction here, these bonding angles are going to basically reduce as they come downwards. So here we have a 4th atom entering. It's going to form a bond to the central atom. And this bond having formed has repelled these other electron areas downwards. And so we have formed the new molecular shape, which is called a tetrahedral shape. And this tetrahedral name comes from the fact that it forms a tetrahedron if you go to each of the outer atoms. Now an example of this is methane, so CH4. And the bonding angle of the central atom, so we've got the HCH bond angle, is now 109.5. And that's all due to the space that this extra area of repulsion is taking up. Because in trigonal planar it was 120, and now it's occupied 109.5, which is lower. Now, if we were to take these 4 areas of electron density, but swap one of them out to instead be a lone pair, then what happens is there is a change in the bond angle. So we're going to have to pause for a moment and think of the effect that lone pairs have on the bonding angles. So the first thing to know about lone pairs of electrons is that they cause extra repulsion. Now the reason for this is that the lone pairs are closer to the central atom because they're not involved in a bond, and so they take up more of the available bonding space. So as a result, they will repel any other neighbours more so than a bonding pair. So if we were to just look at our central atom and call it A, and then put 4 areas of bonding electron density around it, and on the end of those, let's just put some atoms that we're going to call B. Then we've created a tetrahedral structure with each of these bond angles being 109.5. Now, if we start to explore this idea of the lone pairs producing more repulsion, let's switch out one of these atoms for a lone pair of electrons. With this introduction of a lone pair, we're going to have more repulsion between this lone pair and the bonding pairs, so the angle of the lone pair A and B is going to be greater. And this will be the same for any of these angles, B, A, lone pair, B, A, lone pair. So these are all going to be greater than 109.5. But because these are occupying 3-dimensional space, as this angle increases, the angles BAB decreases. So we have a reduction in the bonding angles. And this is the same for any BAB bond. The actual bonds that is formed when this is reduced is 107 degrees. And actually, this gives rise to a nice rule that each lone pair that's introduced to a molecule reduces the angle between the bonding pairs of electrons by 2.5 degrees. So as you can see in this tetrahedral structure here, with the 4 areas of bonding electron density, the angle is 109.5. If we use this rule here, on introducing one lone pair to the molecule, we have decreased the 109.5, take away 2.5, we get 107 degrees as our bonding angle. So using this rule, we can relook at this scenario where we've got 3 bonding areas of electron density and 1 lone pair. If we refer to the tetrahedral structure where they were all bonding pairs, then the introduction of 1 lone pair is going to reduce our bonding angle by 2.5 degrees. An example of a molecule that adopts this shape is ammonia, NH3. So you can see this area at the top here has been replaced by a lone pair. We've got 107 degrees, and the name of these are called trigonal based pyramids. So the trigonal part comes much like trigonal planar from the fact that these 3 atoms, or the bonding areas of electrons, produce a triangle on the bottom. And then if we extend that up to our lone pair here, we actually create a pyramid. Now, in the next example of 4 areas of electron density, we're going to have 2 of those being bonding areas and 2 of them being lone pair areas. An example of this is water, H2O. Now, in this example, it's worth noting that actually oxygen is the central atom here, so it doesn't quite follow our rule that seems to work for most other examples where the first element is the central atom. So if we just draw the water molecule, it's going to form a similar shape to the tetrahedron. So I'm going to draw the oxygen in the middle and the 2 hydrogens on the outside, just like in methane. And the lone pairs of electrons on the oxygen are going to adopt similar to positions to the hydrogens in methane. The angles follow the same rules here. So if we use 109.5 as our starting point, we've introduced 2 lone pairs of electrons. So that's going to be 2 times a 2.5 reduction in the bond angle. 2.5 for each lone pair. And so we're going to end up with a bond angle of 104.5. This shape that is produced is known as nonlinear, and sometimes it's referenced as V-shaped also. Now if we look at the next set of examples, here we've got 5 areas of electron density around a central atom. We're going to look at the example PF5. This goes back to the first atom of the formula being our central atom, so we're going to put that in the centre. The way the 5 fluorines arrange themselves around this central atom in 3-dimensional space is going to be to get the different bonds as far apart as possible. So actually what it does is it adopts for the first 3 fluorines, it's going to be like a trigonal planar type molecule. So at this viewpoint, we're looking almost directly at the phosphorus. This fluorine's coming towards us, this fluorine away, and this fluorine in the plane of the screen. And the angle there is just like trigonal planar. We're going to have 120 degrees between the F, the P, and the Fs. These atoms and how they're arranged are known as equatorial atoms. And it's a bit like looking at a globe and you've got the equator. These are around the equator of the phosphorus. And then what we need to do is introduce the following 2 fluorines, and these adopt axial positions. I'm going to draw 1 on the top of the phosphorus and 1 on the bottom. Now the angles of these are different. So these FPF angles are actually 90 degrees. And that's the case for any of the angles between the axial fluorines and the other fluorines involved. So this is 90, this is 90, this is 90. There's obviously a similar situation happening for this fluorine also. So the two angles that you need to learn for this are 90 degrees and 120 degrees. And the name of this structure, this shape of molecule that's produced, is called trigonal bipyramidal. So the trigonal part of it comes from the fact that these three fluorines make a triangle. And bi means two, pyramidal is our pyramids, because we can create two pyramids from this triangle, one below and also one above. That particular shape is not as common as some of the others. The next shape that we're going to look at with 6 areas of electron density around the central atom is an example of a very common one, especially with transition metals. And what we're going to look at is the example selenium hexachloride. So selenium is our central atom. And this time we need to arrange the 6 chlorines around the selenium to get as far away as possible in 3-dimensional space. Now, once again, we're going to put 2 that are axial, so we're going to put 1 above and 1 below. And the 4 that remain need to be as far away as possible, so we're going to create a square on the equatorial bit. This is known as square planar if they were just on their own. Then drew the first 2 chlorines coming towards us, and the other 2 final chlorines going away. You can see how that creates a square on the equatorial part, and then you can see how if we created sort of a square based pyramid on the top and the bottom, we get this sort of arrangement. And this leads to the bond angles between each of these Cl-SeCl bonds, so whatever you look at, they're all going to be 90 degrees. And that's true for all bonds. Now, the shape of this molecule is known as octahedral. And whilst there are 6 atoms around the central atom, oct comes from the fact that there are 8 faces. So if you see each of these triangles that form from this octahedron, we have 8 faces. So all of these shapes that we've looked at concludes the common different types that you get. You need to be able to, basically in an exam, identify whatever molecule you're given, how many areas of electron density there are, work out which of those are bonding pairs and which are lone pairs, and those pieces of information will allow you to deduce the correct structure. Okay, now we're going to test if you can use this information in this grid format on a couple of different examples. So what I want you to do is basically use the formula to construct a displayed formula for that particular molecule, and then work out how many areas of electron density there are, how many within that are bonding pairs, and how many are lone pairs, and then use that to deduce the shape and the bond angle. So pause the video here and have a go at these different examples. So first of all, just going to show you the different displayed formulas for each of these different examples. Now, if for whatever reason you couldn't get these structures, for example, question 4 and question 5 here, through actually changing the formula into a displayed structure, then pause the video now and still have a go at the skill we're trying to practice today. But if not, I'm going to start to reveal the answers and just give a quick explanation of which. So the question 1, first of all, here we have beryllium iodide. This is linear, as we have 2 areas of electron density around the central atom, and so the angle is 180 degrees. Question 2, we've got boron trichloride here. So boron's our central atom with 3 atoms on the outside. This is trigonal planar, and our angle is 120 degrees. Silicon tetrachloride, we have 4 areas of electron density. They're all bonding pairs. So this is going to be tetrahedral with a bond angle of 109.5. Question 4, our central atom is carbon, and there are 3 areas of electron density. So remember to take into account as a double bond, there's still one area of bonding electron density. So we have a trigonal planar shape around the carbon atom, and the angle around the carbon atom is 120 degrees. Now we have to be specific about the actual carbon atom that we're looking at here, because these carbon atoms, if you were to draw out all the bonds around here, actually have 4 bonding areas of electron density. The 1 here and the 3 between the carbons and the hydrogen. So these will actually be tetrahedral with 109.5 around this carbon atom. So just be really specific and check in your question that you're looking at the right one. And finally, we've got sulfur dioxide here. This is the correct line diagram for it. And what we have here is a linear molecule, much the same as beryllium diodide, and the angle is 180 degrees. So now we're just going to turn our attention to an exam style question. Firstly, you are given the formula here, because this was actually given earlier on in the question. You need it for the first and second part. And also this question is going to allow us to look at this sort of wordier questions that come with shapes of molecules that can often be quite a lot of marks. So pause the video now and have a go at it. Okay, so we're going to go through the first bit. So in order to answer the 4 marker, we need to come up with a dot and cross diagram for the hydrogen sulfide. So we're going to start using some knowledge of the periodic table to construct this. So firstly, sulfur is in group 6, so we know it has 6 electrons in its outer shell. And hydrogen is technically, obviously not exactly in group 1, but has 1 electron in its outer shell. At this stage, you should be comfortable with basically coming up with a dot and cross diagram. If not, make sure you find the video on covalent dot and cross diagrams. So sulfur is in group 6. It needs 8 electrons in its outer shell. There's 2 hydrogens in the formula. Each of them can provide 1 electron. So it's going to share these electrons to get the whole 8 outer electrons. We just arrange those 6 electrons for sulfur, like so. And then take our hydrogens, which have 1 electron for each of them, and just put those electrons as sharing. So we've now got basically a bonding pair here and a bonding pair here, and we've got our 2 lone pairs here. This first part allows us to answer this 4-mark question here. So in terms of this 4-mark question, the first thing you should always state when dealing with any shapes of molecule question is that electrons want to repel to be as far apart as possible. Now, I can't stress enough that this is such an easy thing to memorize, but in so many answers, you don't see this sentence. So ensure that you are remembering this sentence and to always include it when talking about shapes of molecule, because that's one of our 4 marks already hit. Now, the next mark is going to be to state that we have 4 areas of electron density. And then we're going to just drill down into this and say that 2 of those areas are bonding areas and 2 of those areas are lone pairs. And that gives us our second mark. And then using this information, then we know that with this information we can deduce the shape and the bond angles. So the shape of this is going to be non-linear. And remember that the bond angle for this is between the S, the H, and the H. So it's a HSH bond. And with it being non-linear and the fact that it's got these 2 lone pairs of electrons, then it models itself on the tetrahedral structure, which has bond angles of 109.5. But because we swapped 2 of these atoms with lone pairs, then we are reducing the bond angle by 2 times 2.5 degrees. And so we have the bond angle of 104.5 degrees. And so as long as we comment about this in our answer, we've got that 4th and final mark. Now it comes to know that you could just learn these shapes. You don't need to understand the principle behind it in this respect, but it can help in terms of learning it. So this video has covered Year 1 shapes of molecules. All that remains is that if you found the video useful, ensure that you like the video, ensure that you subscribe to the channel in order to get updates of the latest videos to help you understand the A-level chemistry concepts in a clear and concise way with lots of practice questions to check you've understood it.